Alright, so we are now going to start the third chapter. It's named primes and their distribution. And the first section is about the fundamental theorem of arithmetic, which you may probably already know. It states that any integer greater than 1 has a prime factorization. That's what it essentially states. We are going to see what the actual statement is, but the section starts with the definition of prime numbers, which is also well known to us. So the author puts it in this way: an integer p greater than 1 is called a prime number, or simply a prime, if its only positive divisors are 1 and p itself. No other positive divisors are there. If that happens, then it's called a prime number or simply a prime. And an integer greater than 1 that is not a prime is termed composite. So among the first 10 positive integers, these are the primes. 2, 3, 5 and 7. And these are the composites: 4, 6, 8, 9 and 10. So you can see that 2 is the only even prime. In fact, we are not just talking about these 4 primes, but among all the primes, 2 is the only even prime. Any other even integer, by definition, has to be composite. And 1 is, by our definition, neither prime nor composite. Why is 1 not included in this definition? That can be a question, and the answer lies in the fact that the factorization of every integer greater than 1 that you get from the fundamental theorem of arithmetic, that has a uniqueness also. Namely, the primes that appear in such a factorization are the only primes. There cannot be some other set of primes which will also give that a factorization of the same integer. So that uniqueness will be violated if 1 is, for example, allowed to be a prime. And to get rid of such problems, it has been decided to not consider 1 either as prime or composite. Okay, it does not matter if we exclude it. So that way things remain neat. So let us now see, before we go and see the actual statement of the fundamental theorem of arithmetic, there are some preliminary results that we need to prove first. And one of them is the very important property of prime numbers, which is the next thing that we are going to prove. But before we state the property, you can notice one thing. In an example, let us see what that property is. You look at the integer 36. It can be factorized in several different ways. For example, you can write it as 2 times 18 or 3 times 12. These are not decimal points, okay? When you write a decimal point, it appears at the bottom. These are appearing in the middle. Or 6 times 6. How else? Yeah, 9 times 4. and you see that the prime number 3 divides 36. That means 3 is dividing each of these products. 3 divides 2 times 18, 3 divides 3 times 12, and so on. And in each case, you can see that 3 divides at least one of the two factors. Here, for example, 3 does not divide 2, but 3 divides 18. Here, 3 divides both of them, 3 as well as 12. Here also 3 divides both 6, they are the same in this case. Here 3 does not divide 4, but 3 divides 9. And this property of primes, that whenever a prime divides the product of two integers, then it has to divide at least one of them, is not shared by composite numbers. For example, let me give one such example also. 6 is composite, okay, and 6 divides 2 times 3 because that is also just 6. But 6 neither divides 2 nor divides 3. So this property distinguishes prime numbers from composite numbers. Now we are going to prove that this is in general the case, and that is the next result. And in fact, it is so important that it's a theorem. So let's see. So that it just simply says this: if P is a prime number and P divides AB, although the author doesn't write explicitly what A and B are, let me just simply write where it's understood, but still just in order to be complete, where A and B are integers, then P divides A or P divides B. And note one more thing, that whenever we use OR in mathematics, the logical connective OR, if nothing is mentioned, we mean inclusive OR, which means that something is true or something else is true or both are true. If you want OR to mean exclusive OR, that either this is true or this is true but not both are true, then you have to write that explicitly. In general, OR means inclusive OR, which is the case we have here. For example, here 3 divides 3 and 3 divides 12, okay. Here, however, 3 only divides 9, so that's why we are using inclusive OR. Inclusive OR in fact occurs more often than exclusive OR, so that's why we have decided to keep this symbol for to mean inclusive OR. Okay, so now how do we prove this? Right, so what is our hypothesis? Our hypothesis is this divisibility condition, that P divides AB. Now, if P actually already divides A, then of course there is nothing else to do. If P divides A, then we are done, because that is one part of the conclusion. So let P not divide A, then the greatest common divisor of P and A is equal to 1. Okay, how is this coming from this condition, this non-divisibility? That is because p is not just any integer, but p is a prime. And being a prime, p has only two positive divisors, 1 and p. And we know that the GCD of any two integers is a positive integer after all. And in fact, it has to be a positive divisor for both the integers. So if you are thinking of GCD of p and a, then it is something which is a positive integer and it has to divide both p and a. In particular, it has to divide p. So that means, since p itself has only two positive divisors, so this GCD actually can only be either 1 or p. But if this GCD is equal to p, then since GCD is supposed to divide both the numbers, so p has to divide a, then in that case, which however is not the case. So that is why this is not true. So that means we should have the only other option, that is GCD of p and a must be equal to 1. But then by Euclid's lemma, p has to divide b. Do you remember Euclid's lemma, which we proved in the previous chapter? It says that if a is a non-zero integer and b and c are two integers such that a divides bc, and GCD of a and b is 1. That means a and b are relatively prime. If these two conditions are there, then that implies a divides c. In that case, a has to divide c. Okay, so we are using that here. So that is Euclid's lemma. So that's it. If p divides a, fine. But if p does not divide a, then p has to divide b. So that means either this is true or this is true, or maybe both are true. So that's the proof. And now this result has a very simple and natural corollary. Actually, there are two corollaries. The first one is this one. If p is a prime and p divides such a product where these are integers, then p has to divide at least one of them. P divides ak for some k where k lies in this range. So that means this corollary is a natural generalization of this theorem. In this theorem, we have only a product of two integers. Here we have a product of any number of integers. And the natural way to prove this is by induction, of course. We apply induction on n, the number of integers in that product. The result is trivial if n is equal to 1, because in that case it's just the statement that P divides A1, then the conclusion is also P divides A1. That's why it is trivial. In that case it's true, it's already true. And the case n equal to 2 is just this theorem. The case n equal to 2 is theorem 3.1. So let's now assume our induction hypothesis. Let the result be true for a product of n integers where n greater than or equal to 2 is some integer, some arbitrary but fixed integer, and n greater than or equal to 2 because we have already seen the case 2. If you want, there is actually no need to explicitly write this case n equal to 2 separately. You can start your induction here with n equal to 1, and then straight away you can consider the induction hypothesis. That way also you can proceed. Now let B1, B2, etc. Bn plus 1 be integers such if you want you can take a1, a2 and so on also, but I just want to emphasize the fact that these ai's are general things. Okay, so it's not meant to the statement does not mean that some a1, a2 up to an are given and then you are taking another integer. No. In your induction hypothesis, whatever you are assuming is an assumption on n. There only n is fixed, but the actual integers themselves can change. Okay, so it's an assumption about any such set of n integers. That's what it means. Any such list of n integers. So that's why we have just simply taken some other in n plus 1 integers bi's, such that P divides their product. Okay, then by theorem 3.1, so we are now going to use theorem 3.1 here, treating this product as a product of two integers, one of which is this single bn plus 1 and the other is this product. So P has to divide either this product or bn plus 1 or both. P divides B1 times B2 times B3 up to Bn, or P divides Bn plus 1. Okay. Now if P divides Bn plus 1, then we are, or let me just write, then we stop. Now this is looking very weird and foolish. Instead, let me write like this. If this is the case, if P divides this product, then by our induction hypothesis, P divides Bk for some k where k lies in this range. That means if this is the case, then P divides some Bk from these n integers. Or if this is the case, then of course again P is dividing some Bi. Hence P divides some Bk. Yeah, we can write here also we can write k, because k is after all a variable, where now k lies in this range. So this completes the induction. And the proof also. And now this corollary one, there is another corollary after this, in which we are going to now take the integers also, some special kind of numbers, not just any integers. This is corollary 2. Let P, Q1, Q2 and so on, Qn be all prime numbers. And suppose that P divides the product of these other n prime numbers. Note one thing carefully, that nowhere are we saying that these are all distinct. No, that is not what we are saying. In fact, the Qi's themselves may not be distinct. In fact, all the Qis may actually be the same prime. The only condition that is given is that P divides this product. Then already we know by corollary 1 that P divides one Qi, but even more than that, actually P is equal to Qk for some k where this. Okay, let's see now how this can be proved. So we immediately know that from the conclusion to corollary 1, we have this. Why? Since this is already given, P is dividing QK for some K where K lies in that range. Now note that since P is a prime, so P is by definition a positive integer. That is dividing QK, and QK is also a prime. But we know that since QK is a prime, it has only two positive divisors, 1 and QK itself. This cannot be 1 since it's a prime, so by definition P is greater than 1. So that means P has to be equal to QK. So let's now write these things. Since P is positive, we can write at once, since P is positive. Even a stronger condition is this. Since P is greater than 1 and QK is a prime, because of these things we must have P equal to QK. So that completes the proof. Now we can go to the fundamental theorem of arithmetic. Now you know that in this book the author tells about the history of these things here and there in many places throughout the book. So here also, in fact in the beginning, even before these results come, the author says that proposition 14 of book 9 of Euclid's Elements has this result, which later came to be known as the fundamental theorem of arithmetic. So it is coming from there. And what it, we know what it says. It says that every integer greater than 1 can be broken down into a product of primes. And that's it. Primes cannot further be broken down into anything in a non-trivial manner. So that's why primes become the building blocks for all integers if we follow the process of multiplication, if we consider the multiplication operation. That way, primes are the things that are used to build other integers, all of them. So naturally, primes themselves become very important, and it's a central question as to how these numbers are arranged on the number line. What is their arrangement? What is their distribution? That's a very deep and very big question. And plus, there are many other properties of primes, many properties that have already been proved, but there are many others which have not been proved. So they have always intrigued mathematicians and people who like mathematics, and they are doing it. The thing just goes on. They are very mysterious. In fact, one of the best unsolved problems, I must say, arguably the best, and the most difficult one is the Riemann hypothesis. and that somehow is related to the distribution of prime numbers. But anyway, let us now see the statement of the fundamental theorem of arithmetic. So this is the second theorem, and it's just called that fundamental theorem of arithmetic. We have many other fundamental theorems in mathematics. For example, you have the fundamental theorem of algebra, then you have the fundamental theorem of finite abelian groups. So a theorem is called fundamental if it says something central to a part of mathematics and where things start. Okay, so this is one such result, and it's just this: every positive integer n greater than 1 is a product of primes. Okay, can be expressed as a product of primes. This representation is unique. Except for the order in which the prime factors appear in such a product. You can change the order, but you cannot change the primes themselves in the factorization of a given integer. Whatever primes you have found in such a factorization, they are going to be the only primes. You cannot bring in another prime from outside in which the prime factors occur. So let's now see the proof. Sometimes the proof is done by induction, by using strong induction. Here, however, the author has just done it in a different manner. Okay, so so n is already given, so we can start with n. If n is itself prime, then we are done, means there is nothing else to show. Actually, the proof starts with another line. I forgot to write it, but let me just simply say it. It starts like this: since n is greater than 1, so by definition 3.1, either n is a prime or it is a composite, and that fact comes from the definition. Then we write, if n is itself a prime, then we are done. We are done at least in showing that there is such a representation, that n can be written as a product of primes. So if n itself is a prime, then there itself this fact comes out. So let n be a composite integer. Okay, now composite means what? Composite means by definition an integer greater than 1 that is not prime. And what is the meaning of prime? Something is called prime if its only positive divisors are 1 and itself. So that means if we are saying that n is composite, that means it will have some positive divisor other than 1 and itself, because 1 and itself are always going to be positive divisors of n. So there should be an extra positive divisor. Then there exists an integer d such that d divides n, d is a divisor of n, and d satisfies this inequality. So d is positive, and also d is different from both 1 and n. Thus, we have n equal to there is no need to consider this equation. Instead, we are going to consider the smallest such integer d. You see, we have found one divisor of n which is a positive divisor, and that is different from both 1 and n. But that does not mean that this is the only one such positive divisor. Maybe there are others. Whatever the case is, there will be a smallest one. Let P1 be the smallest among such positive integers d. But why should it exist? Why should there be such a smallest positive integer? That is because of the well-ordering principle. You see, you can consider the set of such integers d. Because these are positive integers, that set will be a subset of the set of positive integers. And because there is at least one such d, that set will be a non-empty subset of the set of positive integers. So by the well-ordering principle, that subset will have a smallest element. That smallest element is P1. It exists, that means P1 exists by the well-ordering principle. In this book, the well-ordering principle has been considered as an axiom, as a property of integers, positive integers, that we already know is true. It has not been proved from something else, say the principle of mathematical induction, but one can do that. In fact, using the well-ordering principle, the mathematical induction has been proved. They are actually equivalent to each other, so you can consider any one of them as your axiom, and the other can then be proved as a theorem. Okay. Now we can write our factorization of n in terms of P1. So P1 divides n, so after that division something will be left out, let that integer be n1. where n1 is a instead of explicitly writing positive integers, n1 is an integer satisfying this. Okay, can you see why n1 is greater than 1 and not equal to 1? That's because if n1 is equal to 1, then n will be p1. But we have considered n to be composite, not a prime. Okay, so that's why n1 is greater than 1. But at the same time, n1 is less than n, because if n1 becomes equal to n, then p1 has to be equal to 1, which cannot be true, because p1 is a prime number. And whatever we did with n up to this stage, we can now do it with n1. If n1 is a prime, then we have our representation. Because if n1 is prime, then we have realized n as a product of two primes. If that happens, it's conditional. But if n1 is composite, then we can repeat the above argument to produce a prime P2 such that n1 is equal to p2 n2, where n2 is an integer satisfying this. We then have n equal to, n was what, p1 n1, but n1 is this, so n becomes p1 p2 n2, where we have this. Continuing this process, we will get a sequence n3, n2, n1 such that we should mention that this is a sequence of integers. a sequence of integers, in fact a sequence of composite integers, because the process does not stop if the number that you ultimately have is still composite. So as long as we are getting composite integers, the process continues. A sequence of, well, this is a very, I should not have written this. The sequence does not look like this, but instead it should look like this: n1, n2, n3, and so on, of integers such that but obviously this sequence cannot have infinitely many terms, since this sequence is, or rather to emphasize the fact that it just simply is not but has to be, finite, we will reach, okay, there is a lizard, it's going to disturb us, but let's just concentrate on this. We will reach an integer nk, say, in the above process, that is a prime. And when we reach this nk, then by that time we will have this factorization of n. So n is equal to p1, p2, etc. So looking at these things, you will see that this is pknk. Having gone through the process this many times, you will reach this, but then it's no longer possible for nk to be composite because you have run out of space. So nk has to be prime, and when that happens, you have then found a factorization of n where all the factors are now primes. This is a representation of n this is a representation of n as a product of primes. So you can see that this proof is not an induction proof actually. Induction can also be used, but the author has followed a more, an approach which is easier to understand, which is more intuitive and less formal. And there is one other thing that one should note. In our process that is giving us this P1, P2, N1, N2, N3 and so on, we are having the n's in this order, the ni's. However, we don't really know that P1 is less than P2 or any such order relation between among those primes. In fact, these primes need not be distinct. For example, if you look at an actual integer, 12 say, then for D, if you run that process here for 12, then say as a divisor of 12 that is positive and also that is different from both 1 and 12, say you found out D equal to 2. You then write 2 times, so this 2 is your N1 and 2 times, 2 is your P1 and N1 is going to be 6. But then when you repeat the process with 6, then you get 2 times 3. Also, you can see that 2 is actually the smallest positive divisor of 12 that is different from 1 and 12. So that's why I chose 2. But then if you run that process with 6, you are again getting 2. So your P1 is 2, P2 is also 2, and that's why in the prime factorization of 12 you have this. P1, P2, these are the same, P3 is something different, P3 is another prime. So you should not be confused in thinking that the primes have to be distinct. No, they need not be distinct. The statement says that all the factors are primes, that's all. But that is just one half. Now we have to prove that this representation is unique in the sense that once we have found some primes, they are the only primes, and we cannot find any other representation having some other set of primes that if you take their product you are still going to get n. No. So that's the part now we are going to prove. Now we prove the uniqueness of the above representation, and in this uniqueness we are of course not considering the order in which the factors are being written. That is, you can write 12 as 2 times 2 times 3 or as 2 times 3 times 2. These are not considered to be two different factorizations. They are the same. So what we are going to do here is we are going to consider two, I won't say different, but two factorizations and then prove that those two are actually exactly the same. So let n be equal to P1, P2, etc. till Pr, and that is also equal to Q1, Q2 and so on to Qs, where these are all primes. And we can arrange the primes. That's because we can change the order according to our convenience. So we can arrange the primes in an increasing order, that we can do. So say this itself is in increasing order. P are. Similarly, the Q's also are in increasing order. S, and there is one more condition that we can assume, that is R is less than or equal to S. Is it justified to assume these things? Because we can change the order of the factors, we can write them in such a way that we have these inequalities, and we have allowed for the possibility that some of the primes may be equal to one another. Okay, so that's why not strictly strict inequality, but less than or equal to. And also in general, I mean, see, when we are considering this, we don't really know whether R is equal to S. They may be different. There may be different numbers of factors besides being different, I mean having different factors in these factorizations. So that's why in general we have allowed for that possibility also, R less than or equal to S. Okay, now we are going to start our argument. Since P1 divides the product of the PI's, of course, because P1 is one of the factors, so it will divide this. We have P1 dividing, if P1 divides this, then since this is equal to this, so P1 should also divide the product of the QJ's. But then here we can immediately apply corollary 2. But then by corollary 2 to theorem 3.1, I am just simply going to write corollary 2 above. P1 is equal to QK for some K, where K varies in this, I mean K lies in this range. But we already know these inequalities, that's how the QJ's are arranged. Hence, Q1 is the smallest Q and P1 is some Q. So that's why Q1 is less than or equal to P1. Now, if you use a similar argument with starting from Q1, whatever you did with P1 and this side, you do a similar thing with Q1 and this side. And then if you proceed similarly, you will end up concluding that P1 is less than or equal to Q1. So a similar argument gives us P1 less than or equal to Q1. This is the advantage of having a pre-ordered list of factors. Okay, so we can have these inequalities, and now we can conclude that hence P1 is equal to Q1. So if P1 and Q1 are the same, then we can cancel those things from both sides of the equation and have another equation which is smaller in size. And so P2, P3, etc., PR equal to QS. Now whatever we did with P1 and Q1, we can repeat with P2 and Q2. Proceeding similarly, we will have P2 equal to Q2, and cancelling them also, we will have still another reduced equation, PR, that is equal to QS. Okay. So how far will this go? You see that because we have already assumed that R is less than or equal to S, we can go till PR. For each PR, we will not run out of Q's here because of this inequality. And because whenever you are, you see, if you go till PR itself, say you have managed to remove all the previous primes, and now you just have PR here, QR here, and then maybe some other things up to QS. So then what you do your argument with PR, and QR is already available, so you can do that other similar argument with QR as well and conclude that PR is equal to QR. But now if after cancelling PR and QR also, which are by then they will have been proved equal, you still have other Q's left, then on one side you will have 1 and on the other side a product of some primes Q's, and that is going to give you a contradiction. So let's write, if it happens that R is actually less than S, then the above process will eventually give us this. But this simply cannot be. But this is absurd, since these are all primes and hence greater than 1. So how can their product be equal to 1? It cannot be. So that means this will not be the case. r cannot be less than s. Thus, we must have r equal to s, and hence, we are assuming that we have run the process till PR, but by that time, when you reach PR and QR and run the process with them also, you have already shown that P1 is equal to Q1, P2 is equal to Q2, and so on, all the way up to PR equal to QR. But cancelling PR and QR now will not leave you with this, but it will leave you with 1 equal to 1, which is okay. And hence, so we have shown that those two factorizations of n are precisely the same. So that's why it's unique. And here the proof finally ends. And I'm going to end the video also here. There are some other things that need to be talked about after this proof, which are there in the text, but we are going to discuss them in the next number theory video. And after that, we are going to start solving the first set of exercises in this chapter. So our next upload is this coming Friday, and on Friday we are going to go back to graph theory. And in graph theory, we have, after so many days, finally reached the end of this current long preliminaries chapter. So that means this Friday we will start solving the exercise problems. So see you on Friday with some of the solutions to the exercises. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.